Okay, so now we're going to move on to talk about liquid chromatography. And I wanted to highlight that first in this video because it's a different separation method. It's still chromatography or separating molecules based on the properties, but now we're going to do so in the liquid phase. Our mobile phase is going to be a liquid. Very important to understand, okay? It's very different. In gas chromatography, you use a completely different apparatus. Now, when you're going to do liquid chromatography, you would use an apparatus that looks like what we see here at the bottom. Let's just provide an overview of how this works. You're going to have a bottle called the solvent reservoir. In that bottle is where your mobile phase is stored. Mobile phase is a liquid. Please note that it can be an organic solvent, it can be water, it could be a mix of the two miscible liquids. They have to be miscible to make it work. But nonetheless, your liquid mobile phase is going to go into that reservoir. It's usually a bottle, about a liter or two in volume. Right there is an inlet filter. It's very common to have that on your tubing. So you filter out any small particles which could clog up or damage your column. The solvent is pumped through a short length of tubing by a mechanical pump. This pump is an important part of the liquid chromatograph. It needs to be capable of providing flow rates on the order of up to maybe 5 milliliters per minute through our column. And to achieve that, because we're going to be using packed columns, we need a very high PSI pressure provided by this pump. Really a few thousand PSI are necessary to pump our fluid through our column, okay? So our pump needs to be able to achieve that, and there are a couple of designs that are able to. Now, the fluid from the pump gets routed to the injection valve. Here it's called the injector, but I call it the injection valve. It's more or less the same thing. It's basically a little valve where we add our sample, introduce it to the fluid flow. Fluid moves on to our chromatography column, which are generally packed columns. Once the separation is achieved through using the stationary phase, which is in that column, we flow the material onto the detector where it can be measured, converted to an electrical signal, and our chromatogram can be read out on the computer. So this is your base setup. Now, there are a lot of different variants of this, okay? One initial variant is that we can either run what's called isocratic mode or gradient elution mode. Isocratic mode is this mobile phase remains the same composition throughout the experimental run. Gradient elution mode, on the other hand, is where we actually change the mobile phase composition over time. We can mix components from two different bottles and different mixing ratios. And this actually allows us to fine tune the mobile phase over time. Now, it's probably not exactly obvious why we want to do this gradient elution or fine tuning the mobile phase, but it actually has the same advantages in liquid chromatography that temperature programming has in gas chromatography. It allows us to elute late eluting substance more rapidly by tuning the solvent strength of the mobile phase. And we'll kind of talk a little bit more about that as we go. But nonetheless, there's a couple different modes. Another thing that differentiates the various different modes of liquid chromatography is this column and the stationary phase within it. We can use a number of different packing materials within that column that separate molecules based on entirely different principles. Many different modes of chromatography have been developed over the years, and we'll talk about and introduce some of them here in the next few moments. Now, I mentioned modes of chromatography. Here's some that just are known to man, okay? The oldest type of column chromatography is based on adsorption. This is not an AB, it's AD. Now, adsorption means sticking to the surface, basically. What happens here is our analytes are going to stick to the surface of solid particles, thereby being retained. Now, the solvent in the mobile phase can displace them, but nonetheless, we can achieve adsorption chromatography. Now, the next two phases, normal phase and reversed phase, are forms of partition chromatography. This is actually directly related to that liquid-liquid extraction model and the like dissolves like model that we learned about earlier, okay? Normal and reverse phase columns basically separate molecules based on polarity. In normal phase, we're going to use a polar stationary phase. In reverse phase, we'll have a non-polar stationary phase. We're just going to do a polarity-based separation. There's ion exchange. Ion exchange chromatography, as the name suggests, is useful to separate ions. We have to have charged particles, ions here. They can be negative, they can be positive. If they are charged, we can separate them, presumably by ion exchange. Next, we have our size exclusion. Here, this is a size-based separation. Some molecules are just the right size to be retained, others won't be. And another type of chromatography, we won't talk much about affinity chromatography, but what this basically is use of biomolecules to separate or filter, really. The way that that works is, biological molecules like large molecules like proteins or enzymes, for instance, have specific targets, right? There are also like artificial biomolecules made from nucleic acids that are called aptamers. And antibodies is another example. So very large proteins that bind very specific molecules, kind of in a lock and key type model. So these biomolecules are really useful because they're perfect to selectively bind a particular substance. So why not use those biomolecules to filter that substance out of a mixture? Sometimes people do that. And if you run that in a chromatographic format, you're basically performing affinity chromatography, okay? So these are our different modes. Let's go through them in a little bit more detail. Let's talk about adsorption chromatography first. Adsorption chromatography, AD. This is where we take a silica or alumina stationary phase. It's SiO2 or aluminum oxide. And what we're going to do is we take these solid particles, small little particles like in micron size, okay, and pack them into our column. Now the fluid will percolate through the empty spaces between these spherical particles, much like there's empty spaces at the orange display in the grocery store, right? There's always this little void with the fluid. The mobile phase fluid percolates through that, carrying our sample through those small little holes. But our sample molecule may have an affinity to stick to the surface. Maybe M is our sample molecule. It may plant itself right on the surface of that silica. This is an example of silica, okay? Plant itself right on the surface and adsorb to the surface. Now, if it does adsorb, it is retained and it will not further move down the column until it desorbs back into the mobile phase. Now, how do we get it to desorb? Well, it just so happens that the mobile phase solvent is able to compete. So the solvent comes in, competes for that site, thus displacing the molecule, and the molecule can move on down its way down the column. So the solvent basically competes with the molecule for this binding site on the surface of the silica. And different solvents have different strengths or abilities to compete and for these sites. And basically there's something called the aleotropic series. That's basically a measure of different solvents and how well they can compete for these sites. We don't necessarily have to go into that, but know that adsorption chromatography works via this mechanism that I've just described, okay? Now the next major class is partition chromatography. This is based on the like dissolves like principle. Polar molecules are retained well by polar stationary phases, and nonpolar molecules are going to be retained by nonpolar stationary phases, okay? And we can do it either way, as it turns out. And to demonstrate this, we can talk about normal phase chromatography. Now, normal phase partition chromatography, we're going to make a stationary phase polar. An example of this might be taking a silica bead, okay? And what we're going to do on the surface of the silica bead is we're going to bond other chemical groups. I might bond like a short alkyl chain, but on the end, I'm going to put like a cyanopropyl group, CN. Short alkyl chain, C triple bond N. Alkyl chain, C triple bond N. And I'm going to have literally like millions of these groups on the surface of the silica particle, right? You get the idea. Bonded all throughout. Now this is chemically bonded or fixed to the silica, so they won't come off. Sometimes that's called a bonded phase. But by having the cyano group right here at the tip, that is a polar functional group, and it imparts a polarity then to my stationary phase. Now remember, this is just one bead. Inside my column, I would have packed billions of these beads, right? There'd be billions of these tiny little beads. They're usually just, micrometer size, maybe 5 micrometer for our purposes here. But there'd be billions of these beads inside of our packed column. All of them are going to be coated with these groups or bonded groups with the cyano group, which is polar. So we've made a polar stationary phase. Now, if I have another molecule that comes along, and let's just say that the other molecule is my analyte and it's polar too. That polar molecule may wish to stick to or partition into that stationary phase material because like dissolves like. Polar molecules will want to stick to that. But on the other hand, if I have a non-polar analyte, and that non-polar comes to the surface where it sees those cyano groups, well, no way it's sticking to that. I'm going back into the mobile phase, okay? So as a result, non-polar molecules will not adhere to the stationary phase, won't partition into the stationary phase. They elute first in normal phase chromatography because our stationary phase is polar and the mobile phase that we're going to use, the fluid that we're going to pump through the column, will generally be more non-polar, right? So we purposely make our two phases opposite, right? Our stationary phase is polar, mobile phase is non-polar. We basically just see where the molecules end up. It's pretty simple. Now, the other type of partition chromatography is called reversed phase chromatography. In this type, stationary phase is non-polar. So we reverse things up and we make the mobile phase more polar. How do we do that? Well, we actually start with a very similar silicate bead. Okay, silica bead. Now on the surface, we need to make something non-polar. So why don't we just make alkyl chains there? So I'm going to bond hydrocarbon alkyl chains to the surface. I'm going to bond alkyl chains to the surface of my particle. Just like that. Okay. Now these alkyl chains are just made of carbon and hydrogen. There's no polar functional groups. It'll be like 8 carbons long, maybe 18 carbons long. And in fact, what I'm quoting here will be called C8 and C18 phases respectively. Basically, it just denotes how many carbons long that alkyl chain is. But they're just carbon hydrogen, like an alkyl chain. They're not polar at all. So this is what makes up our example of what makes up our non-polar phase in reversed phase partition chromatography. So what happens here is if I have a non-polar molecule, non-polar NP, it will partition into that phase and be retained. But a polar molecule, on the other hand, will not. No retention or less retention for polar molecules, okay? Now there's really a couple different types of stationary phases that one could use for a reverse phase experiment. One will be the one I'm telling you about, the type 1. This is where we have the silica particles with the alkyl chains attached. C8 and C18 phases are very common. You can also just have a methyl group. It's, in my experience, a little less common. Another option is that you can use polymer beads made of polystyrene. That can also be used for reverse phase material and sometimes is. But the key guiding principle is that stationary phase material is non-polar. That's what defines reversed phase chromatography. And then what we do again is just use it with slightly more polar mobile phase. Maybe we use water or a polar organic solvent like methanol, acetonitrile. And we also tend to also mix water and these other solvents. So long as they are miscible in one another, we can certainly mix the two. And there's nothing wrong with that. That can adjust the solvent strength and the polarity and give us differential migration or elution behavior, okay? Now down here at the bottom is also some guiding principle type information. And sometimes you're asked to predict the order of elution of compounds in these experiments. You know, which compound would you expect to elute first or reach the detector first, right? Go through the column, reach the detector first. Well, for reversed phase, where we've got that non-polar stationary phase, we think that the least polar compounds, they're going to be retained by the stationary phase and not move as fast. So they're going to elute slowest through the column. On the other hand, the very polar molecules, they're going to dissolve well in the mobile phase. So they elute fastest. So polar compounds fastest, the least polar compounds slowest. So you just basically, if you have to predict the elution order, just make a list in terms of polarity, okay? From the most polar compound to the least, and that'll give you at least a guiding guess at elution order in reversed phase chromatography. Simple as that. Now I send another mode of chromatography is called ion exchange. And as the name suggests, if you're going to be doing ion exchange, we need to separate ions. We need to have charged particles. They can be cations, they can be anions. Just as long as it's charged, we can potentially make this work, okay? So we're going to have ions for ion exchange. So what is this all about then? Well, we're going to take an ion exchange resin, and we're going to make a column out of it. It's basically a polymeric material in which there are surface functional groups in this resin that are basically sort of kept with what I'm calling ion pairing agents, okay? So let's kind of take a look at maybe what we mean by that. So there's this large polymer, and I'm going to not write the whole formula out for that. It's carbon, hydrogen mostly. I'm just going to call that resin. But on the surface of that resin, I'm going to add a charge group. And here it's SO3 minus 1. Okay? It's attached, physically attached and bonded to that polymeric resin. But the resin's got this charge group on the surface. Now that charge group can participate in some chemistry for us. What type of chemistry? Well, since it's negative, that group should be able to bind cations. It can bind positive ions. So maybe calcium sample and it's percolating through the mobile phase, comes upon that site and sticks to it, it's retained and is bound by it. If that's the case, the calcium is retained on that resin just by charge-charge electrostatic interaction, and its progress is impeded through the column. Now, if a different ion comes along in the sample, maybe not calcium, maybe sodium, there's lots of options, right? Sodium can maybe bind there, maybe potassium, maybe magnesium can bind there. But each ion has a different charge, and each ion has a slightly different size. And basically what that means then is that each ion will have differential abilities to bind at that charged site, different tendencies to bind at the charged site. So different ions will be retained differently. And because of that, by providing a flow of mobile phase through our column, we can actually separate the different ions in a single experimental run. Now the sulfite group is one potential ion pairing reagent. There are other groups that we can incorporate. Simple carboxylic acids are also charged. This is the deprotonated form, of course, and they work just like the SO3 minus group. Okay. Now notice that these are both charged, right? So we're going to call, they're charged negative, I meant to say. So we're going to call them cation exchangers, because that's what they do. They exchange cations, they bind cations. Now, would these substances bind anions or negatively charged ions? No, they most certainly would not. Why would a negative anion want to bind to a negative site in our resin? It wouldn't. So I mentioned that we could separate anions, but there must be more to it than what I've already told you. In fact, you could probably logic your way through this and decide that, well, if we're going to separate anions, I probably need something that's positively charged on my resin. So I can build a different resin out of a different material. Maybe it's still polymeric, but at the surface where I need to add these charge sites, I can add different groups, maybe things like this. Okay, and take a look at the structure real fast. I'll try to draw it. So first off, there's a bond to that nitrogen, and I'm going to call this R prime, whatever it is. R is like the rest of the molecule, the rest of the polymer. I need to use one of my bonds to the nitrogen just to tie this charge group to the resin. So that's what I'm going to use, okay? And then in addition to that, I've got 3 bonds to methyl groups, methyl group here, here, and here. 3 of them. This yields this type of arrangement yields a positive formal charge on that central nitrogen. It's called a quaternary amine. It's basically a permanent positive charge, okay? So what we've done is we've created a permanently positive charge group on our resin that anions can bind to. So anions like chloride, formate, small acids that are deprotonated, they can routinely be separated by these types of compounds, which we refer to as anion exchangers. positively charged, and they exchange anions. So anion exchange, cation exchange. We can separate the different charged ions. Now let me ask you this. Could you separate both anions and cations in the same exact experimental run? The answer is no. If you're wanting to separate cations, you have to use a cation exchange column. If you're wanting to separate anions, you got to use an anion exchange column. They're fundamentally different. Their chemistry is different. These charge groups are different. You can't make one separate the other. It won't work, okay? But there's nothing that says you can't have two columns, one for cation, one for anions, and oftentimes that's done, okay? But nonetheless, ion exchange chromatography, very useful to separate or filter ions, basically. The next one I want to tell you about is size exclusion chromatography. This is a separation based on molecular size, the actual physical size of molecules. And because of that, we don't mess around with small molecules because they're all about the same size. It would be hard to separate them based on size. But instead, this is the realm of large molecule separations, like polymers or proteins. Proteins are very large chains of amino acids linked together. They can have molecular weight of tens of thousands, very large molecules. Likewise, polymers are basically repeating units of a snapshot of a molecule, kind of like you copy and paste it over and over again. Again, they can have very, very high molecular weights because we can paste large numbers of these base units together. So these molecules become very, very large. We can separate them by size exclusion chromatography. Now, how does this work? Well, we're going to make a stationary phase out of a material that has very small pores, okay? Sometimes a model for that is like a little cone, sort of on the pore of a particle. Okay, so that's my little cone on a sphere, okay? I have this weird cartoon picture at the bottom, but it's probably better to think of it as a cone, okay? So basically there's these little pores, okay? And they can be very, very small, right? Like nanometer size, molecular size. And the thing is that if a molecule comes along that is small enough, it can actually fit down inside that pore. Now this is my stationary phase. So what I'm doing is I'm percolating my flow of fluid, around these particles through the column. But if the molecule gets down that pore, it's kind of sequestered away. So if it fits in the pore, the molecule can be retained, right? Be sheltered from this mobile phase flow, and it's not going anywhere until it just so happens to diffuse out, and then it can get swept down the column, right? So these pores basically are used to sequester molecules away. Now, the thing is that only molecules which are small enough will fit into the pores and be sheltered from the mobile phase. If the molecule is too big, it won't fit, right? So if the molecule is too big, let's say it's this big, right? Molecule, M for molecule. If it's too big, it's going to kind of come along and, well, it doesn't fit. And it's just going to get swept away in the flow really, really fast, okay? So because of that, large molecules in this technique elute the fastest. Now, molecules which are excluded from the pores completely cannot be retained at all. And if that's the case, that type of molecule that's just too big, it just goes with the flow, so to speak. Okay, it goes with the mobile phase flow right to the detector, not retained at all. But it turns out if molecules are a little bit smaller, okay, maybe small enough to fit into the pore, but maybe not very deep in the pore. Let's say you have a molecule about that size, relatively speaking. You can only maybe get like a quarter of the way down into the pore compared to this other case over here. I'm going to draw. We got this pore, we got the sphere, right? And maybe this other molecule is just tiny and it can get all the way down in the bottom, right? So which do you think would have a tendency to stay in their pore longer? The one that got all the way down to the bottom of the pore, the conical shaped pore, or the one that's just kind of inside, quarter of the way? Well, I think the yellow one, the one that really got down there, that's going to reside there longer. This blue one just has a better chance of diffusing back out into the bulk solution, or it'll get swept down the column, right? But the yellow one might stay in there for a much longer period of time before it finally diffuses its way out and then gets swept down the column. Okay, so molecules which are truly excluded, they will elute essentially immediately with the mobile phase flow. But these other molecules, which are a little bit smaller, they can kind of fit in the pores, we still might be able to fractionate them or get some separation of them. based on molecular size. So this one that only got, a quarter of the way down the pore can probably be separated from this one that got all the way down to the bottom, because there's going to be differences in retention there. And indeed, that's the case. That's what happens. So there's a certain molecular weight range for these experiments, the size exclusion. There's a certain molecular weight range. It's called the fractionation range. Fractionation range. And in this range of molecular weights, we are actually able to separate molecules based upon their size quite effectively. What determines this fractionation range is essentially the pore size, how big those pores are. Okay, and that can be tuned to a certain extent by buying different size exclusion materials with different pore sizes. Now, the really cool thing that I love about this size exclusion chromatography, I think this is really neat. It turns out that if you're working in this fractionation range, you can actually run standards of known molecular weight on your column. Get your chromatogram, and if you can assign each peak in that chromatogram to a known molecular weight, you can then run an unknown sample that you don't know anything about and estimate what the molecular weight of unknowns are just by their retention behavior. You just compare them to the standards, and there's actually a way you can estimate the molecular weight. It's really, really cool. You don't need any fancy equipment. You just can do size exclusion, okay? Okay, so that concludes our discussion of modes of chromatography. Now I want to talk just a little bit briefly about some factors that can affect the elution behavior, or the chromatographic behavior and resolution of our chromatographic bands. And of course, this discussion again, centered on liquid chromatography, LC. Now in gas chromatography, we could temperature program, but in liquid chromatography, we alter the strength of the mobile phase, liquid, by changing properties of the solution. Remember earlier, I said you could run a gradient? Running a gradient, all that is you change the composition of the mobile phase through the run. You change the physical properties of that solution. For partition chromatography, if you run a gradient, you might make the solvent more polar over time. Or alternatively, maybe you make it less polar over time if you're doing reverse phase chromatography. If you're doing ion exchange, you might run a gradient by increasing the ionic strength of the eluent, that's the mobile phase, over time. If you increase the ionic strength, you're increasing the number of ions. The ions in your mobile phase will have a better chance at competing for those charge states in ion exchange. Okay, so by changing the properties of the mobile phase, you can really cause things which are highly retained to be eluted more rapidly. Other things you may be able to alter is temperature, which can affect rates of equilibrium partitioning between the mobile and stationary phase, also diffusional behavior. Another thing that's been popular in the recent decade and a half is changing the particle size. It turns out for particle size, smaller you can make the particles, the better. So chromatographic performance. Smaller particles yield better separations. There's actually a couple of reasons for that. Thinking back to our Van Deemter equation discussion, those factors that affect plate height. Remember two of those terms. One, for PET columns, was the irreproducible flow path, and this idea that not all molecules take the same flow path, okay? Well, it turns out if you make the particles smaller, you can generally achieve a little bit better packing in the columns. So the flow paths that all the molecules experience in a well-packed column can be, the breadth of the flow path distribution can be minimized. In other words, all molecules don't take the same path, but more similar paths, we'll say, okay? And the other big reason that particle size plays a role, vis-a-vis the Van Deemter equation, is that if you make the particle sizes small, okay, let me kind of draw a picture, okay? Compare that to big particles, relatively speaking, okay? Should have probably not drawn that one there. Let me move that a little bit. Okay, If you make the particles small compared to big, if there is a molecule that's sort of down between these particles, I'm trying to draw it in red, right? It could be two cases. Remember, we're percolating the fluid through these tiny little pores, just like the oranges at the grocery store, right? Now, the molecule, this little red dot, that's our analyte. Remember, it has to partition to the stationary phase. Between the stationary phase and the mobile phase, there's got to be that equilibrium partition. That's our basis, right, for chromatographic separation. So if that's going to happen, you got to give it time to diffuse to the surface, right? Now, if these little pores or gaps between the particles are larger, it's going to take a bit more time to equilibrate between the phases. Whereas if these gaps are smaller, which is afforded by the smaller particles, less time is required to diffuse to the surface and establish an equilibrium. And as such, we can reduce the mass transfer term as well by using smaller particle sizes. So smaller particle sizes is kind of a bit of the rage the last decade in chromatography. Everybody's trying to get to smaller and smaller particles. Now people may even get to 1 or 2 micron type particles. We keep trying to make it smaller and smaller and smaller to get better chromatographic performance. There is a downside to that. Pumps need to be able to apply higher and higher pressures, higher fluid pressures. Because if we make those little holes between the particles smaller, guess what? It gets more and more and more difficult to pump solution through those holes. So our pumps are really working out, aren't they? We need a pump that can achieve even higher PSI, maybe tens of thousands of PSI. So we need a special design for our pump. In addition, even if you can achieve that special pump, which maybe you can build, you also have to connect all the tubing. All right, and they usually do that through little fittings that screw together. But at very high pressures, those fittings can even fail. And that causes all sorts of leaks in your system and problems, irreproducible behavior. Nobody wants that, okay? But nonetheless, people have spent a lot of time trying to optimize high pressure, higher and higher pressure liquid chromatography the last decade. We can also change the mobile phase flow rate. Usually at your pump, it's an electronic pump. You basically just walk up to it and you can adjust the flow rate. That changes your linear flow velocity, which we know is an important parameter on that Van Diepter analysis that we considered earlier. Here's an example of gradient elution. And in this particular experiment, we ran, or they, whoever did it, ran this gradient, which is a volume percent, I think, of acetonitrile, if I can read it correctly, over time. So what this figure actually does up in the top right corner is explains to us what is the composition of the fluid. That's the mobile phase, okay? It looks like here between 0 and 10 minutes or so, it was, I think, 30% acetonitrile, as if I'm reading it correctly. And then they ramped it up to 45%. And then I think this is even 80%, if I'm reading it correctly, okay? 80% acetonitrile. So they're really changing the polarity of their mobile phase throughout this particular run. So in this particular run, if I'm just going to kind of zoom in a little bit so we can kind of see it. There's a lot going on here, okay? But there's an isocratic separation of a mixture of aromatic compounds, 1 milliliter a minute on an ODS column, octadecylsilane, so that tells me it's an C18 phase, 5 micron silica, I'm just reading down here at the bottom, that tells us the particle size at ambient temperature, okay, room temperature. And they label the peaks, benzyl alcohol, phenol, a bunch of different compounds, right? I'll list right there. The eluent consisted of aqueous buffer and acetonitrile. The notation 90% B in the chromatogram means 10% volume A and 90% volume B. When you see that terminology A and B, they're just talking about the two solvents and the mixing ratio, okay? And the buffer in the aqueous phase is a phosphate buffer, a certain concentration adjusted to pH 3.5. Okay, so all these different figures and basically what they represent, let me zoom back in. What they represent is more or less the results. It's hard to see because it's not the greatest resolution, but the results for changing the percent B if I remember correctly, was the acetonitrile in the experiment. So if you ran it at what appears to be 90% B in this one, this is the chromatogram. If you reduced it to 80%, you got this one, 70%, you got this one, and then I think this is 60%. You get this one, okay? So let's study these peaks now. Again, same samples, substances 1 through 7, it looks like, or 1 through 8. You can see that if you ran at 90% acetonitrile, you elute everything super fast before the 6-minute mark. But a lot of these peaks are not resolved, are they? So that wouldn't be a great separation just because you get a lot of overlapping peaks. Yeah, it's fast, but they are not resolved at all. So why not change the mobile phase to affect partitioning behavior? Remember, the separation is a reverse phase separation, okay? So it's based on that like dissolves like principle. So why not reduce the polarity of the mobile phase by reducing the amount of acetonitrile to only 80%? Now, if we do this, we can still complete the experiment in just under 6 seconds. It did slow down a little bit. We can maybe resolve a few more compounds, but gosh, it looks like these are still unresolved, right? So why don't we go to an even lower percentage B, acetonitrile, 70%, 30% being the other solvent, which is less polar. Well, in this case, we see real changes. Now it takes about 9 minutes, it looks like. Well, 6, 7, 8, about 8 minutes. It takes about 8 minutes to achieve the entire separation. So the peaks are slowing down. But look at the resolution. We got 8 resolved. It looks like 5 and 6 and 7 are pretty much resolved, but 6 and 7 are still eluting together. 4 is almost resolved from 1, 2, and 3, but 1, 2, and 3 are still overlapping. So lower percent. Now we're at 60%. Okay, slow down the separation because things don't dissolve in the mobile phase and get swept through the column as fast. So now maybe it's 15-minute separation. But gosh, we're starting to resolve things a little bit better. We still don't get 6 and 7 or peaks 2 and 3, but we have 4 separated from 5 and 5 separated from 6 and 7. 8's way off on its own as well. So again, by changing the composition of the mobile phase, we can get better and better separations at the cost of time. Now here we have 50% acetonitrile. Separation has slowed down even more. Now it's almost costing us a half an hour. But look, we're starting to see resolution between peaks 6 and 7 now. They're not fully resolved, but they're getting there. And we can even start to see a little bit of splitting here between peaks 2 and 3 at 50% B. So we're making progress. We're starting to achieve a better separation, again, at the extent of time. And again, if we keep reducing, here's 40%, here's 30%. Now, by the time we get to 30%, we're separating peaks 4 and 5. They're way far apart from one another. But where's 6, 7, and 8? They're gone. In fact, they might be out here somewhere, okay? But I'd have to wait, another hour and a half to see them. So at this point, this low percent B composition or low percent acetonitrile composition, I'm separating things, but the experiment has just gotten way too long, right? And gosh, I don't have to wait an hour and a half or 2 hours each run. And even if these peaks elute, they might be so broad, right? Very difficult to see at my detector. So I'm getting better separations by adjusting the percent B, the mixture. But man, I don't really want to wait half an hour, right? So we can see that the percentage of acetonitrile, solvent B in this case, really has dramatic effects on the separation, right? Originally, when it was 90% B, we got those peaks just washed through the column really fast. Things were not retained much because they really like to dissolve in the acetonitrile. But as we reduce the percentage of that substance in our mobile phase, remember that's a mobile phase component, what happens? The peaks slow down, they start to separate. We start to pull out these slight differences in polarity between the analytes at the expense of time. See, well, I like to separate the molecules, but I still don't want to wait around for an hour and a half to see things, right? So why don't we do gradient elution? And that's actually what's shown over here. So remember I said earlier that this kind of provides us of a map of the composition of our mobile phase. It's commonly seen like this. This is basically a volume percent axis here, a volume percent axis of our acetonitrile. Same substance as B over on this side, okay? So what I'm going to do is I'm going to start off at 30%. Now think back to what happened when I did that over here. 30%, you say, I got this case. I got good separation of the early peaks, but I only got through peak 5, 4, 6, 7, 8. I don't know, they didn't never appear, right? Or if they did appear, that's like after an hour and a half, nobody's going to wait around that long. Okay. Back here, okay. All right, perfect. So we start off at 30% and we wait a few minutes, maybe like 8 minutes. And that allows us to get peaks 1, 2, and 3 to the detector where they're separated. So far so good, but we know if we don't do anything, I mean, we're going to be here like 2 hours, right? So what we're going to do is we're going to now, during the run, change the composition of our mobile phase. We're going to increase the amount of acetonitrile. I think if I'm reading correctly, this is 45% now. Okay. Now again, to remember what happens when we start running up 40, 50%, things start speeding up, right? So that's kind of what we would expect to occur. So at the higher percent acetonitrile, remember these analytes, they're more soluble than that. Indeed, they start slowing or they start speeding up. So we get kind of lucky. We increase the concentration and then peaks 4 and 5 appear after a few more moments, right? And you say, well, I certainly want to see all the way through peak 8. Well, how do I do it? Well, maybe I'll ramp up high to 80% acetonitrile now. And whatever's left in my column, I'm just going to wash it through the column. And sure enough, I get peak 6, 7, and 8 not long after. So I ran a gradient elution. I changed the composition of the mobile phase through a run. Now let's summarize what the net result of that was, okay? Let me erase all this because there's kind of a lot going on, right? Over here on the left, this basically was isocratic elution. When they run this experiment, they always kept the mobile phase the same, 90% acetonitrile, 80, 70, 60, 50, down the line. And what they found was if they went too high percentage of acetonitrile, everything eluted really fast. The experiment was over, but it all came out in a big blob. Nothing was resolved. So they were forced to decrease the concentration of acetonitrile. But when they did, things started to take so long to elute. 60, 70, 80 minutes, and we may not even get great peaks for substances 6 through 8. So we can't win, right? If we go too high a B, everything comes out as a blob quickly. Too low a B, we can't even see the late eluting peaks. But if you are able to change the composition during the run, you could start at a low concentration of the acetonitrile or the strong eluent, the strong solvent, things that dissolve things really well. Start at a low concentration of that until you start seeing some of the early peaks elute resolved. Kind of tease out differences in solubility basically by doing this between substances 1 to 3. Then you got to speed things up. So just ramp the composition of your more strong solvent up. Doing so will allow you to elute these later compounds much more rapidly. You can see we've achieved everything here in less than 40 minutes. This is gradient elution. It maintains resolution in early peaks while speeding up those late eluting peaks, okay? All right, the last video is going to be on hardware for LC, but I'm going to make that a different video, so I'm going to call this one quits. See you soon.